Hello, in this short video I'll try to explain in further details the radiometric dating process I used in the last video. These are some details I am more than happy to clarify, and thanks to your comments I realized I should have explained it better. So starting from this sedimentary rock, for example, I cut a small chunk from the area of the rock I wanted to measure. The neat thing about the banded iron formation is you could be sloppy when doing the cutting because the iron oxide would dissolve almost completely in nitric and hydrochloric acid. And the sediment in between the layers is mostly silicate sand, so hydrofluoric acid will be needed to dissolve that. The acid juice is dissolved because we want to match the concentration when injecting it in the mass spectrometer. I use 1% nitric acid, so I diluted my samples 1 to 100. Nitric acid is pretty clean, but because I use hydrochloric acid for the digestion, I had to check the blank first. It doesn't have much uranium and lead in it, but it has enough to skew the results a little bit. And then that's it. The sample is ready for injection. You can directly inject your sample in a mass spectrometer. An ICP-MS is the instrument of choice for this analysis, and borrowing one from an environmental lab, for example, is easy enough, just as long as you misplaced a few nickels. Anyway, because we are looking at raw ratio, there is no need to do any calibration beyond the normal daily tuning. The only thing I did is to set up a method to include the isotope I wanted, increase the dwell time from 50 to 100 milliseconds, and added replicate for a better RSD. If you need more details about doing analysis on the mass spec, let me know. So there's the raw data on an Excel spreadsheet. You can immediately see how much crap is in the hydrochloric acid compared with the rinse, which is only nitric acid. So let's look at uranium-238. The top layer has 8,169 counts, minus the 10 from the blank is 8,159. Next, the corresponding lead-206 has 5,094 minus 902 is 4,192. Now adding the lead-206 value to the uranium-238 value, and you get 12,351. That is our total original uranium at T equals 0. This equation describes the relationship of the number of decaying nucleus as a function of time. N0 is the number of uranium atom at T equals 0. This is the 12,351 we just calculated. N is the current number of uranium atom measured by the instrument, which is 8,159. Lambda is the nuclear constant of uranium, which is the invert, the half-life expressed in seconds. And that's it. All that's left to do is to solve this, and we get to 2.67 billion years. Uranium-238 and lead-206 works great here because there is enough uranium and lead, and the window of time is appropriate for this isotopic relationship. Thorium hasn't really begun to decay much, so that didn't work out too well when I tried it. Uranium-235 doesn't work either for two reasons. There isn't much to begin with, and its half-life is way too short for this measurement. So I hope this video answered your questions. Let me know. YouTube is a great platform for social interaction, and this is a great example of constructive criticism. Thank you for the challenge.